Hello, everyone. I want to introduce the first speaker of our session today, Ben Lund. He's working at IBS Group in Korea. And today he's going to talk about Kakeya and Furstenberg sets over finite fields. Thank you very much.
Yeah, thank you, Tong. What I'll discuss today is joint work with Manekdar and Zevdir. So Kakeya sets over finite fields were just to make sure you can see my slides. Yes, okay, good. Kakeya sets over finite fields were defined by Wolf in 1999. We say that a set of points in a vector space over a finite field is a Kakeya set if it contains a line in each direction. Most trivial example of a Kakeya set is a set of all points. This contains every line, and in particular, it contains a line in each direction. So the interesting combinatorial question is, how small can a Kakeya set be? And Wolf's specific question was, does there exist a constant C such that the size of a Kakeya set is bounded below by C times Q to the n? So Q to the n is the number of points in the entire space. And so the question is it true that every Kakeya set has positive density? This was introduced as an analog to the very important Euclidean Kakeya problem, which I won't say anything more about, but it was expected to be a fairly difficult question, but it was resolved using a very simple very simple linear algebraic argument by Zevdir in 2009. He showed that indeed Kakeya sets must have positive density. What I'm going to talk about today is a generalization of this question, really introduced by Ellenberg, Oberlin, and Tau in 2010. Here we say that a set is a Km Furstenberg set, or K-plane Furstenberg set, if for every k-dimensional linear subspace W, there's some translate of W is intersects the set in at least m points. So here we're generalizing it in two different directions. One, we're replacing lines by k-flats. And the second one is that we're saying that instead of being contained in the set, we only require that it intersects the set in at least, or instead of saying that this k-flat must be contained in the set S, we say that the intersection of the k-flat with S is at least m points. So here a Kakeya set is a 1Q Furstenberg set because for any line through the origin, there's a translate of that line that's contained in the Kakeya set. And so in particular, its intersection with a set is at least Q points, or exactly Q points. And so again, the interesting question is, how small can Km Furstenberg set be? So just to talk about the special cases first, we have the classic Kakeya problem here. The best quantitative bounds are due to Dvir, Kaparti, Saraf, and Sudan in 2010. And up to a factor of 2, the construction meets the lower bound. So for general M, we would say that the line in a set S is a Furstenberg set if there's a line in each direction that intersects the set in at least m points. And here there's 2 lower bounds. The first one is exactly the same lower bound as we have for Kakeya sets. The second lower bound is kind of the trivial lower bound. Here, this comes from counting pairs of points. So if we have a set S, suppose that S is a Furstenberg set, then there are S choose 2 pairs of points. Now, since it's a Furstenberg set that intersects a line in each direction and at least M choose 2 points, so there are more than Q to the n minus 1 directions. And in each of these directions, we've accounted for M choose 2 pairs of points. And this is the sort of trivial lower bound. And these 2 lower bounds meet when M is square root of Q. So this is kind of the most interesting point. there's a construction that shows that this, in general, this lower bound can't be improved without some additional assumptions. This uses this works for square order fields. So suppose that we're in the n-dimensional vector space over FQ, where Q is P squared, where P is some power of a prime. And suppose that we have a set S that intersects a line in each direction in at least P points. Then there's a construction that is of psi order P to the n points. This construction relies critically on the existence of a subfield of order P. And Zhang showed in 2014 that there must be a gap for prime order fields. So if this subfield doesn't exist, you can prove a better lower bound. Certainly this lower bound is not tight, and there remain a lot of open questions around. I mean, really, this example should be the only case in which the general lower bound is tight, almost the only case in which the general lower bound is tight. But this is what's known for the Furstenberg sets. The other direction of generalization is just replacing lines with k-planes. So here we say, suppose that you have a set that contains a k-plane or a k-flat in each direction. A fairly straightforward generalization of de Vere's argument shows that when k is larger than 1, such sets must be, when k is larger than 1 and q is large relative to n, such sets must be nearly the entire space. You can't say very much over the trivial construction of just taking all of the points in the space. But for some reason that I don't want to get into today, the direct polynomial argument doesn't really work very well in the general case. It works fine for when you're dealing with lines with m points on it, and it works fine when you're dealing with k-planes where the entire k-plane is contained in the set, but it doesn't work fine when you're dealing with k-planes and you have only m points on it, and m is much smaller than, say, q to the k minus 1. So the first kind of non-trivial result in the general case was by Ellenberg and Ehrman in 2016. They proved a kind of algebraic generalization, considered an algebraic generalization of the combinatorial problem, and the combinatorial corollary to their result is this lower bound of m to the n over k. And with Dar and de Vere, we showed that you can take, we made some minor improvements to their proof and showed that you can take in this proof, you can take the constant to be something like 2 to the n log n over k. And that's really best possible. Not exactly best possible, but the general form of constant to the n log n over k is the best possible. But it's best possible for the algebraic generalization that's considered in that paper. It's not best possible for the combinatorial problem that we're really that I've described here. So in a separate paper, we've given a number of other results on the problem. First is this, which is very similar. Again, it's m to the n over k. Here, the constant is 2 to the minus n, which is, and really these bounds both are considering more general questions than the one that I've talked about, and they're really incomparable. But you can see that this one is actually a general, it is a kind of if you take k equals 1, then you can recover exactly the known lower bound for Furstenberg sets. So it's a true generalization on that end. But if you can take m is equal to q to the k, which is the largest possible. So if we have m is equal to q to the k, this is the k-plane Furstenberg set. The bound that we have here is 1 over 2 to the n times the number of points in the space. And that's very far from nearly all of the points in the space, which we know is the correct answer in that case. So this works, so it's clearly not tight in all in all regimes of parameters. And in fact, we have an improvement for the case that M is fairly large. So here we're requiring that M, which is, so the statement here is that if we have a set that intersects a k-plane in each direction at least m points, and that M is at least, let's say 2 to the n times q over epsilon squared for some epsilon that you can choose, then you have the set must contain nearly m times q to the n minus k points. So the restriction on M means, well, number one, we can't take k is equal to 1 here because we have more than q points in each k-plane, and q is the number of points in a line. And number two, the size of the field has to be very large relative to the dimension. If, say, 2 to the n is much larger than q to the k, then there's no way that we can contain 2 to the n times q points in a k-plane. So these are some non-trivial restrictions on the set of parameters where this applies, but when it applies, it gives much stronger results than the previous theorem. And in fact, it basically meets a completely trivial construction. The construction is take any set of m times q to the n minus k points. Now observe that if you have a direction w or a k-dimensional linear subspace w, then the translates of w partition the space into q to the n minus k disjoint k-planes. If we have m times q to the n minus k points, then one of those k-planes must contain at least m points. Hence, we're getting a kind of, for relatively large m, when we're getting a very strong dichotomy where when you have much less than m times q to the n minus k points, there don't exist any Furstenberg sets. And when you have more than m times q to the n minus k points, every set is a Furstenberg set. So we have some fairly sharp transition between there are no sets, Furstenberg sets, to every set is a Furstenberg set based on the size of the set. Now what I'd like to do with my remaining time is just give a sketch of the proof of this theorem for large fields. So the one on the screen now. Let me first just review some notation. Here, the cube binomial coefficient is the number of directions, k-dimensional directions in fq to the n. So it's the number of k-dimensional linear subspaces. And the number of k-flats, which a k-flat is a translate of a k-dimensional linear subspace, is q to the n minus k times k choose n, n choose k. Well, that's not n choose k, I'm sorry. The times this q binomial coefficient, n over k. The main tools that play a role in this proof are the Kakeya bound of De Vere. So we kind of use that as a black box, and some incidence theory for large sets and finite fields. Given a set S of points and a set L of k-flats, the number of incidences between S and L are the number of pairs of a point in a flat, such that the point is contained in the flat. And there's a bound that was first proved by Hammers in his 1979 thesis, which says that, well, what this says in some sense is that the number of incidences between a set of points and a set of k-flats is close to the expectation when the sets are very large. So here, if you take a random point, fix a k-flat and take a random point, the probability that that point lies on that k-flat is q to the k minus n, because there's q to the k points on the k-flat, and each of those you hit with probability 1 over q to the n. So this q to the n minus k times S times L is the expected number of incidences that you would have if you took your k-flats randomly and your points randomly. And what we have on the right is some error term, or it's another term. And when it's not necessarily an error term. When the term to the right of the inequality is larger than the expected number on the left, you still get an upper bound on the number of incidences. So there's kind of two regimes. In one regime, you say, well, the number of incidences has to be close to the expected number of incidences, no matter what you do. And in another regime, you get an upper bound, which is still non-trivial. So another an immediate consequence of this is that if you take a set of a large number of k-flats, and each of these k-flats contains has a lot of incidences with some set S, then you have to have a lot of points. Otherwise, we have an upper bound on the number of incidences that just depends on the number of flats and the number of points. So if you have a large number of incidences, you're going to have a large number of points. And here's the kind of the particular formalization or the particular parameters that we're going to need that capturing that intuition. We fix two constants, delta and gamma greater than 0. Now we're going to take a gamma proportion of all of the k-flats and say that each of those k-flats contains at least a delta proportion of all the points. So this q to the n minus k times q binomial n over k, k-flats in total. We're taking a gamma proportion of those. And on each of these, there's q to the k points, and we'll take at least a delta proportion of these. Now the claim is that the overall set S has to have at least some complicated constant times q to the n points. And here, if we need to choose gamma so that this kappa, which is gamma times q to the k, is fairly large. This means that the second term in this constant, well, it's getting divided by kappa, but it also has a square root of delta term and it's being subtracted. So if delta is small and kappa is small, then we may end up with a negative lower bound here. So in general, we're going to want to choose kappa to be something that's larger than 1 over q to the k. And there's also some restrictions on what we can have delta to be in order to get, but depending on what delta and kappa are, in the best case, this could say that we have at least almost delta times q to the n points. So just by requiring a density, if we take a sufficiently large set of flats and require that each one has a density delta, then in fact, our entire set has to have density nearly delta in the entire space. So just applying this theorem without any use of the polynomial method, we can get some non-trivial results for our original problem for flats of sufficiently high dimensions. So here we're going to say that k is large, at least n half. So we're dealing with subspaces that have at least half the overall, more than a half the overall dimension. And we say that each of these contains endpoints, and here we can, we're going to need m actually to be fairly large as well. But in this case, we get the result of the previous, we get the result that we want, which is that we have nearly m times q to the n minus k points without any, without even using the polynomial method at all, and without using the assumption that it's a Furstenberg set even. Here, the only thing that we have is that we have a large set of flats that each contains a large number of points, and we're not using the directions at all. So here and in particular, that we're kind of restricted. What we have to do, we still have to worry about the case that the k is between 1 and n over 2, or that m is larger than the bound that we showed before, which is q times 2 to the n minus k, roughly, and smaller than q to the n over k. And in this range, the idea is that we're going to use the Furstenberg property of the sets to find a large family of k-1 sets that each contain many points of S. And then we'll apply the same argument again with using that lemma, which follows from the incidence bound. So we're going to proceed in basically two steps. First, we're going to find a large set of k-1 flats that are contained in the flats associated to the Furstenberg set. So the definition of a Furstenberg set is that for any k flat, for any direction, there's a k flat in that direction that contains at least m points. Well, let's forget about m for the time being and just look at the set of flats that's associated. There's some family of flats f, that one in each direction, that gives us the Furstenberg set. And let's look at this family of flats. And what we're going to say is that there are lots of k-1 flats in that family of flats without saying anything about how many points of the Furstenberg set they contain. And here and this is where we use the polynomial method, or we're not really using the polynomial method. We're just using the bound on the Kakeya set as a black box. And what we do is we fix a rank k-1 subspace, so some direction, and we're going to show that there are a large number of k-1 subspaces parallel to this fixed subspace lambda that are also contained in the flats of F. The way we do this is, well, let's take the intersection of our flats of F with some subspace p lambda that intersects lambda in a point. We're choosing the dimension of p lambda so that a typical subspace of dimension p lambda is going to intersect lambda in just the origin. And the only thing that we're doing is we're not choosing a set where the intersection is too large. Or we're not choosing p lambda where the intersection is too large. Now, the k-1 flats parallel to lambda, of course, intersect p lambda in points. And you can prove, in a few lines, you can prove that the flats of F intersect p lambda in a Kakeya set. So the points of this Kakeya set corresponds to flats in the direction of lambda. And when we sum over, so when we look at this bound, what we have is the number of directions times the number of points in a Kakeya set of an appropriate dimension. So k, q, n minus k plus 1, 1, q to the k. That's exactly the lower. We can just plug in the lower bound on the size of a Kakeya set that we have from De Vere et al. And n over k-1, the q binomial coefficient is the number of directions. So for each direction, we show that we have a Kakeya set worth of k-1 flats lying in that direction. We still need to show that many of these k-1 flats are going to contain a lot of points. So that's the other part of the argument that we need, is that the lower bound on the number of points contained in each k-1 flat. And here we're going to use another incidence type bound that actually follows. You can prove it from the previous one that I showed without too much trouble. Here we're going to say that a flat is T poor if it contains fewer than T points of S, and it's T rich if it contains at least T points of S. The theorem that I proved with Shirvangi Saraf a few years ago is that if we have, let's take a set of points in the k-dimensional vector space over FQ. So the reason I'm using K here is because we're going to apply this inside the flats of F, the flats that are associated to the Furstenberg set. So suppose that we have a K flat that contains M points and a parameter delta between 0 and 1. Then the number of k-1 flats that contain fewer than delta, that contain at most delta times m over q. So m over q is kind of the expected number of, like, let's say you've got a k flat, you've got a k-1 flat. Now you choose m points randomly. What you expect is that there should be m over q points. So this is saying those that contain fewer than a delta fraction of what you would expect if in the random situation is at most this expression here. And Q times K over K minus what's on top is the total number of K minus 1 flats, and what's on bottom is a fraction that typically is going to be not much larger than 1. So if we choose delta fairly small, we're going to get most of the flats are if we take delta fairly large, then we're going to get most of the flats are not poor. So here's a lemma with a lot of parameters, but what we're doing here is saying that, well, we found a large family of K minus 1 flats that are contained in our K flats. And then we're going to use the previous lemma that I showed to show that very few of these K flats are poor for an appropriate choice of parameters. And consequently, we have a large number of R-rich K minus 1 flats, where R is, say, this number again, and delta is a parameter that we can choose appropriately later. So the proof is exactly what I said. By lemma 2, we have many K minus 1 flats that are contained in the K flats that define our Furstenberg set. And by the theorem proved with Saraf a few years ago, for each K flat, there can't be very many K minus 1 flats. So it's a question of choosing the parameters so that when we subtract the largest number of poor K flats that we can have from the number of K minus 1, when we subtract the total number of poor K minus 1 flats that we can have in all of the flats of F from the number of K minus 1 flats that we know must be contained in the flats of F, that there's a lot left over, and these have to be the rich K flats that we were looking for at the beginning. So this is the theorem that we wanted to prove. If you have, if M is large, then our Furstenberg set S has to be nearly as large as possible. And so again, the sketch of the proof, omitting all the calculations, is that we know we've already managed to find a large number of K minus 1 flats that each contain a large number of points. And we know that if you have a large number of K minus 1 flats that each contain a large number of points, then the underlying set has to be large. And this is, again, an application of that incidence bound from the very beginning. Let's see, how much time? I think that's all the time that I have. Is that correct, Thong?
You have 1 more minute.
1 more minute. So I'm just going to skip the entropy formulation and I'll skip talking about the other result and simply end. So thank you very much for your attention.
Thank you very much for the talk. So question for speaker, please. So I have a very simple question. So suppose if you consider R that is not a set of point, but you consider a set that is a set of, let's say, H planes. So for some H and H much smaller than K. So do we think the same idea works?
Yeah, maybe. I haven't really thought about the question before. I'd have to think about it. Yeah.
Thank you. Any other question, please? Okay, so if there's no other questions, so let's thank speaker again. Thank you very much.
Thank you.